All right, hello everyone. This is our class number 21. We are going over random forest applications. Well, actually, how we can apply it using Python, right? So I'm going to go over two different Python notebooks. The first one is random forest regression, and the second one is random forest classification. For the regression, we're going to work with the Logan housing dataset. So this is a dataset that we're all familiar with. We have worked with in the previous homework. And now we're going to apply random forest and compare it with, I think we applied SVM to Logan housing dataset, right? And we're going to compare the outputs of SVM versus random forest when it comes to working with this Logan housing dataset. Okay, so without further ado, let's go over the Python notebooks and then see what we have. So running the libraries, loading the data. So this is our data set. Just as a refresher, you're interested to, this is a regression model, right? You're interested to predict the house price. We do have the sold price. This is a labeled data, right? We have days on the market. These are the features: garage capacity, HOA fee, irregular shape. These are categorical ones, quadrants. Okay, and the school district, sold term, total bedroom, total bathroom, total square feet, year built, zip, year sold, month sold, and the built after 2000. The reason that we added this dummy variable at the end of the day was because if we wanted to use year built as a dummy variable in the model, we had lots of years built, right? I think we can look at the exact numbers. Let me see. Year built. We had 136 of them, right? So it's going to increase the dimensionality of the data a ton if you just add year built as a dummy variable, given the fact that we don't have enough observation for all of the 136 dummy variables. So for that reason, we said that, okay, let's go ahead and make a dummy variable, call it built after 2000. And if it is after 2000, call it 1, before 2000, call it 0. But now that we're using random forest, we know that random forest is not forced to make categorical variables necessarily into dummies. So it's going to remain one variable. So this is awesome, right? So for that reason, we're going to get rid of build after 2000 for random forest and work with the more informative variable, which is year built. Do you see the trade-off, what I'm trying to do with the data? Okay. Okay. Then there are 4,000 something observations. There's no null. The data set is very clean. Actually, we're working with the clean one. There's no, well, the only thing that we needed to be aware was there were a couple of observations which were duplicated. We can get rid of them by running these drop duplicates and in place is equal to true, just replacing the data. And now we look at the unique numbers. So sold price, this is continuous random variable, days on the market, continuous, garage capacity. Again, this is continuous. We can, when I say continuous, I mean it's not categorical. It can be integers, right? HOA fee. So these are categoricals: irregular shape, quadrants, school district, and etc. So we have sold term, and these are total bedroom. Sorry, bedroom, bathroom. We can treat them as numericals. We don't need to be worried about that if they're categories or not. But what we need to fix before running random forest, I know that random forest can handle categorical data. Can actually do it perfectly. But the thing is that the algorithm cannot handle strings, cannot handle words, right? So we have to make sure that, and these are called ordinal categorical variables, right? Is everybody familiar with the terminology? So we call them ordinal categorical variables. So for example, we have quadrants, we have school district, and we need to make sure that instead of these strings, we're going to use numbers, 0, 1, 2, 3. And that number can be anything. It can be 100, 200, 300. It can be -3, -2, -1, anything, right? As long as you're consistent throughout the code, you should be good. Now, in order to do that, we're going to use another encoder from the scikit-learn pre-processing class, right, module. So let's look at that encoder. I call it, well, let's encode ordinal categorical features as an integer array, right? So we are going to go ahead and change this irregular shape, quadrant, school district, sold term, and that's pretty much it, right? Zip, well, also zip code, right? Because I don't want to, if I pass this one as integer to the model, well, I think for the zip, we don't necessarily need to do that. Yeah, we don't necessarily need to do that because if it is a, let me see, what is the type of the zip code? it's already integer. So I can get rid of this part as well. It really doesn't matter. But if you do it, it's not going to hurt. So if the point is that if categorical variable is already integer, fine. If it is not integer, you have to do this step. You have to encode it. So we're going to use this ordinal encoder from Python pre-processing module. And then again, we save it as an object. And off of that object, we can call a fit transform. So this is exactly like standard scalar fit transform, normalization fit transform. Here, the ordinal encoder fit transform, and then we pass the data. And I'm going to pass the entire data set, not the trained versus tested, because we need to make sure that for the entire data set, these string categoricals are transformed to numerics, numbers, integers, right? Now, if we do that, look at that. I can, off of that object, I can call what are the categories. So the categories for, what do we have? We have no and yes. For irregular, sure. For quadrants, we have northeast, northwest, and etc. And it's by default, it starts from 0. You can change that default number, right? You can say, okay, start from 100, start from 200. By default, start from 0. So no is 0, yes is 1. So 0, 1, 2, 3. In the data, when it comes to quadrants, if I see 1, it means that it's northwest. Okay. Then we have cache, Logan. These are, I think, school districts. Yeah. And then we do have sole term, cache, conventional, FHA, other, and rural development, VA, and VA. So 0, 1 up to, let's see, what do we have? Sole term. So we have 4, for example, 0, 1, 2, 3, 4. This is USD rural development. All right, USDA. Then we're ready. Now the data is ready. We can now pass this to our algorithm without being worried of normalization or standardization, or without being worried about making categorical variables into dummy variables. This is a huge thing, right? So why I say this is huge? Because look at the size of the data. Well, actually, let me go ahead and, oh, I haven't run this line. Oh. I'm going to go ahead and drop this built after 2000 as well. If I look at the shape of the data, there's only 15. One of them is target variable. So actually the number of dimensionality of the feature space is going to be 14. In the previous homework 8, when you were working on the same data set coming up using the SVM, we ended up with 58 features, right? So look at the chain, you know. You can imagine if I want to look at the results of the same model using KNN, it's going to do a very poor job because the dimension is high, it's 58. But now random forest can handle it with only 15 features, 14 features. So this is important. Okay, scaling the features, we don't need to do that. We're going to set random state is equal to 1000, defining our target and the target and feature space, and splitting the data with a test size of 30 versus 70 train size. So let's go ahead and do that. So this is the core of the model, right? So this basically four lines. We're going to import the random forest regressor from this scikit-learn ensemble class. So in the ensemble, we have random forest classification, random classifier, random forest regressor, and etc. So this is one of the ensemble methods that we're going to use, random forest classifier. We will, as always, we're going to start with the very basic inputs, the default inputs of the. Well, actually, let me pull up textual help. So let's look at the inputs of the random forest. So these are, we talked about the hyperparameters of the decision tree. So let me talk about the new things, right? So the number of estimator, this is a new thing. This is our B, capital letter B. How many trees you want to make out of that data set, right? And then criteria, this is regression. So we have MSE, max depth, mean sample. So these are all this, we have seen all these things. So there is this thing which is new, bootstrap is equal to true. So by default, it's going to generate the new trees based on some bootstrapping, right? Resampling from the train set with replacement, right? And this is out of bag score. So do you remember we talked about, actually, I have a Python code for you ready. You will see that numerically, at least you will see that 2/3 of the observations are going to be in that bootstrap sample, and 1/3 is going to be what we call it out of bag, right? I'm going to show you a numerical example. It's very straightforward. Then random state. Why do we have random state in random forest? Where do you think that the algorithm is using that random state? Where's the randomness in random forest? Yeah, split, right? Actually, a couple of things. When the algorithm is deciding what subset of the features it's going to use, right? It's going to do that job by let's say randomly, and where to put the split. Again, these are all random things. At least the initial point is random. So the reason that I put random state is equal to 1000 here is that if you want to get exact same number as mine, so you should put the random state here. For your homework, I want you to specifically use one specific random state, because this is for just the sake of reproducibility of the work, right? This means that if I don't put the random state here, every single time that I run the model, the outputs are going to be slightly different. All right, and then we talked about, look at that, even in random forest, we can do the cost complexity pruning method. And this is the alpha that we talked about in last class. And yeah, that's pretty much it. Let me have a word with you about the bootstrap. So let me actually try to pull up these slides. This is important because this is one of the, at least you can, if you don't want to use those sophisticated variation of the random forest for time series, you can at least do some basic stuff which control for those effects, right? So let me show you what I mean by that. Okay, so when we're doing bootstrapping, look at that. If it is time series, do you agree that it is completely changing the order? Fifth observation, imagine these are times, and 2020, 2017, 18, it doesn't make any sense, right? If I reorder. So if you want to apply the random forest to time series, at the very least, there are lots of things you can do, but at the very least, you have to turn that bootstrap feature off. Does that make sense? Because you want, so what's the difference? The difference is that the model is going to always use the entire data set, not a bootstrap version of that. And there is no out of bag observation. It doesn't make sense to have out of bag observation, but the splits are going to be still random. So random forest is going to still decorrelate the trees less than bootstrapping, but still it's going to do a better job than decision tree. Are you following that? So this is only if you want to do time series. So if you want to do time series random forest, again, it's a little more subtle than that. There are lots of things that you should be aware of, but at the very least, make sure that the bootstrap is false. And you cannot believe how many people make that mistake, even in academic papers. They just simply apply random forest to time series, which is absolutely false. Yep, Ryan.
Can you go back to the
Imagine
it's going to keep the observations in order, but it can grab different
splits. Yeah, so it's going to be feature 1 and 4, but 1 through 5, 1 through 5, 1 through 5. Okay. And again, it is not the best. It's not the ideal thing, because remember, you wanted to decorrelate the trees as much as possible. If I do not randomly select them and maybe something, for example, leave some observations out, so it's not going to decorrelate it that much, but it still is better than decision trees. Decision tree is this. If I look at this entire data set and make a tree out of that. But I'm going to use a subset of features, and it's going to help reduce the dimensionality at each weak learner, which is a good thing, right? It's going to speed up the process. Good. And so that was one thing that I wanted to emphasize. Let's continue. Okay, so let's fit the model to the train set, and let's look at the predictions. We call it y hat. We can look at y versus y hat side by side. So these are the numbers, and these are the sale price, right? For example, for this observation, $234,500, and the prediction is this number. It's not bad off. Well, actually, when I look at this one, the predictions are not bad off. But again, let's continue and look at more formal measures like R-square, like RMSE, and etc. So let's evaluate the model on the test set. We're plotting y versus y hat, and we know that if it lines up across this 45-degree line, it's a good sign, right? Because y is closer to the y hat. So we have, there's clear sign of heteroscedasticity going on here. Well, it's if I look at the residual, I can see the heteroscedasticity a lot easier, but it seems that at the higher tail of price, the model is having a hard time making predictions, right? So maybe if you use a log transformation combined with random forest is going to do a better job. Okay, if I look at the R square, so R square for the very basic model, the not optimized random forest is 84%. So it's not that bad, right? And if you compare it to the not optimized R square from the SVM, which you did for the homework 8, the answer was 73. So right off the bat, I think it's 10% improvement in R square, which is a good thing. And again, I'm not worried about the adjusted R score. This is machine learning because this is an R score in the test set. It automatically takes care of that feature that why we should use adjusted R score versus R square. Okay, then I can look at the RMSE in the test set. So this is the RMSE in the test set. What is the unit of the RMSE in the test set in this example? What? Dollars. Very good. Yeah. So because our target variable is sold price, so the RMSE unit is dollars. The unit of the MSE is dollar square, which doesn't make any sense. So that's why we report the RMSE. All right, now let's tune the hyperparameters, and we're going to use Gridsearch. So let's, I think I received I got an email that it was a very good question. It says that, how do you know that what values for the hyperparameters you start with, right? So why do you pick 10, 100, 500? Why not, I don't know, 1,000, 200, 2,000, something like that? Well, what you see here, I run bunch. Yeah, I usually start with 2 numbers for each of these hyperparameters and see which one is performing, and then I find the direction. So I'm randomly doing that, but somehow you have to do educated guess, right? And I show you the best combinations. So if you're doing it here or for the homeworks, and this is not necessarily the best of the best because maybe I'm stuck in the local optimal, right? But as we talked about it, this random search is going to do a better job than some gradient descent approaches, right? So that was a good question. So number of estimators, we're going to go with 10, 100, 500. So what is number of estimator? That capital B, how many trees you want to make. So 10 trees by default, I think Python used 100. And maximum feature, so this is our M. M is the square root of P or log to the base of 2 of P. If I put none, well, if I put none, what is this? The random forest is going to become bagging, right? If M is equal to P, the random forest is exactly equal to bagging. So let's go back to the lecture notes here. If M is equal to P, the random forest and bagging are the same. At each split, it's going to look at all the features, 1, 2, 3, 4. But if M is less than P, then we call it random forest. Okay, this is just naming. Yeah, I think you can call all of these things random forest. Okay, so I know that we can get the model can do a better job. Either I use a square or log to the base of 2. And then finally, I look at max depth of 5, 10, and 20. If I do not restrict the model this way, it's going by default, it's going to use none, which is going to start with a very bushy tree, right? So if the max depth in your grid search turn out to be none, you have to put it though, right? So you have to. The reason that I didn't put it here because I tried with none and I saw that okay, the smaller numbers are going to outbid the none, so I excluded that one. But for the homework, I think you should put none and see if the random forest decides to start with a very bushy tree or small tree. Okay. Here, let's go ahead and run this. And this is going to take, well, we have 90 different fits, right? Because I think I use cross validation 5. So 5 multiply 3 multiply 2 multiply 3. If you do the math, math is going to be 90. And then we will be looking at the optimal parameters. Let me see, did I put a random state here? Yeah. So if I did not put the random state here, then every single time that I do grid search, it's going to give me maybe different answer, right? But if there's a clear cut between the features regardless of the random state, is going to always give you one output. But if you want to get exact same answers that I get here, just make sure that you specify what is the random state. Okay, I think the optimizer is done. Yep. And the best parameters are max depth is equal to 20. Max features is SQRT, the square root, and number of estimators 500. So it's not the default one, right? Because the default one is 100. All right. Now let's look at the y-hat optimized version. So we're going to predict off of this optimized model, which we call it Gridsearch. Now compare the three outputs together, right? This is my y-hat optimized. And now I can visualize the y-hat optimized versus y, actual versus the predicted, the optimized version. Look at that, I'm using the optimized version. And so if you compare this one with the other one above, so remember, without doing any optimization, the R-square was 83%, right? Up here. R-square is 83, almost 84%. With doing all these trouble, Gridsearch, and etc., we could improve it only 1%, right? So maybe just again, the default features of the random forest were doing a decent job. Usually when your accuracy in classification or R-square in regression are high numbers, you cannot optimize it further, usually, okay? Unless you change the engine, you change the entire model, right? But that's the case, especially for random forest and boosting. You'll see that if you're using the default inputs and you get an accuracy or R-squared of 90%, the odds that you can improve it a ton is small. Okay. All right, then we can look at the MSE in the test set. All right. So that's pretty much it. This is how random forest can make predictions. And I think Sarah pointed out the other day, okay, now I have a model which is trained. What can I do with that? You can make predictions. So that's the whole reason that so now how can I make predictions? I make it, I don't know, I make a new, let me actually show you. I come up with a new data set, right? Let's say I come up with 5 new observations and I have to fill in all these things except the target. And then I pass that to the fit. So I say, okay, what do we have here? Random forest regressor. And I do dot predict, then pass my X test, let's call it new. This X test new is something that you have to construct manually and pass it to the model. Then so for example, imagine this is the, without the sold price, because it's not labeled, you want to make predictions. I pass this data set and the output of the model is going to be 5 numbers, 1, 2, 3, 4, 5, whatever it is. Okay. Okay. Compared to numbers before using, okay, so this is here I just compared yeah, we talked about it, that the R-square did not improve a ton, so it improved but very slightly. So here's a recall for you. The best we could do with SVM was R-square 80% and random forest is 84%. So SVM was also doing a decent job, even though the dimensionality was 58, right? So it's just good to know. Sometimes 4% is a lot, right? Remember that Netflix Kaggle competition, they were looking for a couple of percentage increase in accuracy for $1 million, and the price was $1 million, right? So, all right. Now we're gonna estimate this number. Let's say I want to estimate this 84%. Guys, this is the R-square in the test set. Does everyone see that? This is the R-square in the test set because we're using the predictions in the test set. These are the y-hat optimized and the y in the test set. So this is my R-square in the test set. How can I estimate this number? There are 2 different ways. The first method is using cross-validation. We know that we can use cross-validation to estimate the performance metrics in the test set, right? Another one, which is unique to random forest, is what's called out-of-bag estimation, out-of-bag errors. So let's start with the cross-validation. So if you're familiar with cross-validation, we're going to call this cross-val score function. And then the score at the end of the day is going to be R2. So if I pass R2 and pass my, let's say my optimized tree, let's say this is the optimized tree, and then pass it to the cross-val score, and then run this line. It's going to take a little time, depending on how many folds you want to So I'm looking at 5 folds, but remember 5 folds, 500 trees. So already I'm talking about 2,500 trees, right? And then again, even with that, you see the random forest is relatively fast when the sample size is small. So here we have 4,000. Then I can look at this R squared cross-validated. Remember, R squared cross-validated is an estimated version of the R squared in the test set. So 78%, in the test set it was 84%. So this is more conservative. If you want to report one number, it's going to be this number, right? If you're writing a paper, you want to report the estimated R square or performance of the model, you have to report the cross-validated versions, right? Because that's more reliable. All right. So the second method to get this number, to estimate this number, is this 84%, is out-of-bag errors. So here's the part that I promised you I'm going to show you with numerical example. We can show that on average, each bagged tree make use of around 2/3 of the observation. So let me go back. So this is a bagged tree. How many observations do I have here? 5. Each tree, so how many observations do I have here? Can you tell me? 3, right? So 1, 3, and 4. So I have 3 observations here, 3 observations here, 3 observations here. Okay, roughly, again, I'm going to numerically show it to you. 2/3 of the observations from the train set is going to be in these trees, the bagged trees. 1/3 is what we call out of bag. So do you agree that if I use the out of bag, I can treat them as something that the model has not seen? Is it, and if I report the performance metrics on that, is it a fair estimate for the performance metric in the test set? So for that reason, actually, it's going to do a very decent job, by the way. Let's see if we can get a number close to this one, because this is the estimated version from the cross-validation. Here's, and you don't need to run this. This is just well, for the sake of understanding it better. So imagine I'm using this random method from the NumPy, and let's say I'm using, these are random numbers between 1 and 100, and I'm picking 100 of them. So between 1 and 100, these are the, let's say these are the random draws from the observations, right? Okay. Are you following? So this is exactly this. So if I use 5, so maybe the outcome is going to be 1, 1, 3, 4, 3, right? So look at the output here. So we have 82, so 80-second observation. The first draw was 82nd. Then 3, 40. There are some repetitions here. So if you pay attention more carefully, some of them should be repeated, right? But I cannot find one here, but yeah, lots of them. Well, we're going to use Python to tell us what percentage is repeated, right? So these are, out of these 100 numbers, I'm going to ask, report me the unique ones. Look at that, 60 of them are unique, 63 of them, 61. Well, let me use control. If you do this process over long run and take the average, the answer is 2/3. Does that make sense? So 2/3 of the observations are going to come from the parent distribution, and 1/3 is going to be out of bag. Okay. And now, how can we make these things in Python? It's very easy. Whenever you're constructing your random forest regressor, just make sure that you pass this out of bag score is equal to true. Because by default it's false. By default it's false. Look at that. If I set that equal to true, then behind the scene, the algorithm is going to report those out of bag and then perform whatever metric that you're interested. For example, if you're interested in R square, in regression, it's going to report the R square for out of bag observations. In classification, it's going to report the accuracy of out of bag observations. And by default, as far as I know, by default, these are the only 2 metrics that out of bag observations. This random forest classifier regressor is going to do it automatically for us. So if you want to, for example, see what is out of bag F1 score, you have to manually construct, as far as I know. Okay, I have to double check, but I couldn't find it in the Python documentation. By default, if you call this score, out of bag score, for regression, it is R squared. For classification, it is accuracy. Are we good? Okay. And the process is very easy. If I just change this out of bag score equal to true, and then I call it. because guys, remember, this is my object. I call it RF out of bag. If I do dot tab, so these are the options that I can think of. For example, I can look at this is the path of cost complexity prune path. We can look at what else? Well, the one that we are looking at is the score. Yeah, out of bag score. So we can report this number. Look at that, this number, 78%. 78%. This is doing a pretty decent job, right? So then you might ask, okay, which one should I prefer? Should I prefer work? Well, actually, let me ask you, why do you think, even if when I have cross-validation, because we know I personally trust cross-validation a lot more than the out-of-bag, right? Even though out-of-bag is going to do a decent job. But my question to you is that when you have this beautiful cross-validation method, why do you bother to report out-of-bag errors to get an estimate for test set errors or test set R-squared? Why do you think? What's the motivation? Let me give you a hint. Which one is faster? The out-of-bag is a lot faster, right? Yeah, it's already there, exactly. And the reason that by default this feature is off, because we just want to make sure that we speed up the process. Okay, so guys, remember, by default this out-of-bag score is false, because if I set it equal to true, it's going to do further calculations behind the scene. Good. Okay, now let's talk about feature importance. I think we don't need this contextual help anymore. So feature importance is something that we could call off of the decision trees as well, but we didn't, because decision trees usually we prune it a lot back. We visually look at the tree, so we knew that which split was the most important, which feature was the most important. So for that reason, I decided to talk about feature importance here in random forest, but be aware that decision trees as well can report the feature importance. Okay. So we're gonna in order to construct the feature importance, first I'm gonna save them, save the name of the columns, the features as features. Makes sense, right? So these are my features: days on the market, garage capacity, and etc. And then we can refit the model with whatever combination you want. So for example, I want to work with the optimized model, right? I can say 500 square root 20 and random state is random state. You can refit it again. And then when you have a fitted random forest model regressor, off of that, you can do dots. And one of the features is called feature underscore importance, right? So if I do tab, these are all the things that I can get out of this object. This is random forest model, right? In R, remember, it was saved as a list, but here is an object. And off of that object, you can call many things. So one of those things is feature importance. So the feature importance in regression analysis is what is it doing behind the scene? It's calculating the total amount of for each feature, it's calculating the total amount of reduction in RSS through over the entire trees, right? So for example, it looks at total square feet, and then they calculate when the model used that split, that feature as a split, what was the reduction of the RSS at each split? Sum it through the entire forest of trees, and then report a number. Okay, so that, of course, in Python, it's just function calling. You just call this method, and then look at the importance. So I call it importance, and then these are the numbers. And the rest of it is just some fancy stuff. You want to sort them. So I'm going to go ahead and make a data frame out of this because I can visualize it easier. I call it the FIM. I don't know, feature importance method maybe. And then this is a data frame. Features are X-train columns. Actually, I've created features here. I could have write features. No, it really doesn't matter. Features. Then feature importance is what we call importance here. And then let's sort them by value, ascending, sorry. And then look at the table. So numerically, these are the numbers. So it seems that, these are ordered now. It seems that total square feet is the most important one, then garage capacity, and the least important one is irregular shape. Then we can visualize it. The reason that I like to sort it, because when it comes to visualization, it's a lot easier to see what's going on, right? And yeah, that's pretty much it. And this is most of the application of random forest. I don't want to say most, I should be careful because I'm interested in asset pricing when it comes to finance, but finance is very broad, right? It has many applications in asset pricing or portfolio allocation, this feature importance. I can look at the weights and then I say, okay, but these are, imagine I have different factors. I can weight the factors based on these weights, right? So something like that. Okay, now let's see. So this is the second part that I wanted to talk about. So does more importance feature means more significance? So do you think that if I run a simple linear regression model, the total square feet is going to become most important, most significant, and the irregular shape is going to become least significant? What do you think is the answer? The answer is, if you're using linear regression model without any tweaks, putting polynomial degrees and things like that, there's a good chance that the ordering is going to change. For some of them, is going to completely change, because we know that simple linear regression model, if you're not adding quadratic polynomial version, it's not going to capture nonlinearity, right? But random forest is capturing nonlinearity. So, however, you can use them side by side, right? So I have the feature importance. So right now, I want you to remember total square feet is the most important, then garage capacity, and etc. Now let's go ahead and use from stats model API. Let's use this OLS. This is our simple linear regression. I have to add a constant. Remember, I think in second week of class we went over these models. So we need to add a constant and then run the model. Look at the output. So this is you're all familiar from our econometric course. We're all familiar how to interpret this table, right? What I want you to pay attention is the t-stat. Which one is the most significant one? Total square feet is the most significant one, right? Which one is the next best? Constant, we don't care, right? So years sold, which one is the next best? Garage capacity, right? So we started with total square feet. So total square feet, yeah. Garage capacity, no, actually the second one was years sold, right? So the second most significant was years sold. But if I go back to years sold here, look at that. It's 1, 2, 3, 4, 5th to the end, right? So there is no one-to-one relationship between significance versus feature importance. But the takeaway from comparison of the t-stats of the linear model and feature importance is that, so for example, I think in the homework, we will see something like that, one of the features turned out to be not significant. So it's not significant at all, but it shows up at the very highest, most important. So what's your conclusion when you see something like that? It is, when you use linear model, it's not significant, but when you use random forest, it's among the top 5 or top 3. What do you conclude?
Linear model must be missing some sort of shape within the data.
Perfect, right? The model is missing, the linear model is missing the linearity, right? And guys, when I say linear model, linear multiple regression model without adding polynomial degrees, right? Yeah, very good, very good. And yeah, let's, I think there was one interesting one somewhere. One of them was not even significant. Let's see, HOA. Many of them actually are not significant. Yeah, HOA fee is not even significant, but it shows up among the top 6, right? 1, 2, 3, 4, 5, 6. Yeah, so this means that most probably HOA has a nonlinear relationship in the data, which your linear model is not able to capture. So this is pretty neat, right? And when it comes to, so I can interpret this one relatively. I can say, okay, total square feet is more important than garage capacity, but I cannot put any numbers in it, any numbers, right? However, I can perfectly interpret these numbers, right? So for example, for, I don't know, total square feet, it says that for every unit total square feet in the property, on average, the price is going to increase by $80, right? We cannot say something like this using random forest. Remember, it's a non-parametric model. The weights, there's no weights, and even if there is, they are going to be completely lost in the forest. All right, so that was the regression part. For the classification, we're going to do it very quick because we did the hard part. We talked about all the features of the model. Are we good for the regression? Guys at home, are we good? Okay. So let's go over the classification example. For the classification, I'm going to work with our credit card data set. This is a clean version. So you guys did a EDA on the credit card data set, and the credit card data set comes from the Kaggle competition. And these are the variables, right? Variables. So the ID, I'm going to drop it out because it doesn't have any explanatory power. Limit balance, sex, education, marriage status, age, pay 1, pay 2. So just as a refresher, what was pay 1, pay 2, pay 3? So pay 1 is the repayment status in the previous month, and pay 2 in the past 2 months, pay 3 past 3 months, right? And the repayment status can be paid in full. We'll pay the minimum amount only. If it is 1, it's equal to delayed for 1 month, 2 delayed for 2 months, and etc. Right? So this is going to have an impact on if a person is going to default or not, right? Then we have balance limit, the same story with the numberings. So balance limit in the past month, in the past couple of months, past 3 months, and etc. And yeah, that's pretty much it. And then payment amount in the past 6 months, past 5 months, and etc. And then if the guy is going to default or not. Before running any model, which of these features do you think is going to be the most important one? Make a guess, and then we're going to see what the random forest decides. If you want to make a guess that someone is going to default or not, out of these features, which one is most important? Definitely not sex, right? Income. Do we have income here? We don't have income. Income was a good one, right? But it seems that we don't have income here. No. What else? Just make a guess. Let's have some fun. And then at the end of the class, we're going to see which one was the most important one. Just make a guess.
Or predicting which variable?
Default. I'm giving you a set of features. Common sense. Limited balance. What else? Age. Okay. What else? Education. Okay. So yeah, we'll see. Well, the reason that your guesses are a little off is that maybe no experience, no background in credit analysis. Usually the payment history is the most important factor. So if your payments is 1 month delayed, 2 month delayed. But anyways, we'll see where limit balances stand, where age stand, where education stand. But just wanted to give you some heads up. All right, so let's go ahead and look at the data quickly. This is a clean version, so I'm not worried about duplicate numbers and etc. But here's the part that the random forest is going to shine, right? So if I look at the number of unique variables for each data set, so for example, pay 1, I have 11 categories, pay 2, 11. So 1, 2, 3, 4, 5, 6. Already we have 64. If I want to make these pays to dummy variables, I'm already adding 64 number to the dimension of the data. But if I use random forest, it's going to be only 6. Okay, the same story but that's it. That's pretty much it. Okay, so again, we're going to encode the ordinal categoricals into integers. Do we have anything that we need to be worried about? I think we do, right? Yeah, we have married, so these are strings. University, these are strings. So we have to change these 3 because that's it, right? Sex, education, and marriage. So let's go ahead and change that. Sex, education, and marriage. Make sure that we use our ordinal encoder to transform them into the numbers. And then just to keep track, you can always run this, give me the categories you want to see if you want to read the data. So marriage is 0. 0 means married, and then 1 means other, 2 means single, right? This is not as straightforward as someone might think, right? Then graduate, high school, other, university, female, male, and etc. You can change these orderings. This is very flexible when you're fitting, you fit transform separately and then just some labels to this function. All right, then scaling, we don't need to be worried. Then let's go ahead and look at the distribution of our target variable. We have 77% no default and 22% default. So it's relatively imbalanced. Well, again, I don't want to be super picky about that number, but let's say we are not necessarily happy with this 20 versus 80, right? We will see what are the options. Random forest has a feature that we can change. That's going to help us out. For your homework, though, I think you're dealing with a data set which is 94%, 6%. So for your homework, you have to make that tweak. Okay. Defining the variable is splitting the data. This is not logistic regression. So I don't need this one at all. So these are the columns. Did I write somewhere? Yeah. Previously, we used logistic regression for the same data set, and it used to have 78 features, but random forest ends up with 23 features. You know, we are economizing, let's say, 50 something observation, which is neat. 50 something dimension, which is neat, right? Okay, now let's split the data, 30%, 70%. Let's import our random forest classifier. The rest of it is exactly the same as regression, so I'm going to speed up a little bit. So fit the train the model, make predictions. However, guys, remember the output of the random forest can be either classes, 0, 1, default, no default, or probabilities, right? So we can come up with probable, because at the end of the day, at each terminal node, so what do we have? Let me see if I can find an example. Yeah, at each terminal node, we have number of observations, which is 0 or 1. We can calculate the probabilities, right? So for that reason, we can come with probabilities as well. So I just want to keep track of both of them. So y hat is 0, 1, y hat probability. These are probabilities. We can visualize the distribution of the probabilities. So this is relatively doing a good job. You know, when I say good job, I'm not talking about the performance of the model. I'm talking about the balance of the target variable. So if the probabilities are relatively spread out between 0 and 1, then you don't need to be worried about that threshold. Do you remember if all of them were here, you have to reduce the threshold to just increase the recall, you know, just reduce the false negatives. So we had this discussion before for classification. But here, I think it's relatively good. So if I use the default threshold, which is 50%, it's going to do a decent job, right? However, in random forest, there is a feature called class weights, and I can change that class weight to balance, and it's going to automatically rebalance the data set for me. So this is a very cool feature. Okay. Evaluating the model performance in the test set. So we're not going to come up with the customized performance metric function for performance metrics. I'm going to use the built-in functions in Python. So we can look at the confusion matrix, true positive, true negative, false negative, false positive. And then we can use a classification report. So F1 score for the default is 48. This is what we're interested in. It's not that high. And accuracy is 82. And precision 66, recall 38. So the recall is 38, and that, of course, if I reduce this threshold, the default threshold is going to increase the recall, but we're not going to do it in random forest. We're going to use that feature of class weight to automatically do it for us. Okay, let's tune the hyper. Is there any question? Let's tune the hyperparameters. And yeah. We are going to, the number of estimator, again, I tried a bunch of different versions, but this one, because it was taking a little longer, just for the illustration purposes, I stick to the default value, which is 100. Criterion, this is classification. We can have entropy versus Gini, max features. Again, you know, you can, at home, you can try different, you know, you can try SQRT, you can try none. Max depth, I just try to keep the trees small as possible, so 10. Even with that, this, by the way, we are talking about 17,000 observation, I guess. Is it that data set? No, I think the number of observation is 30,000. Am I right? I guess so. Yeah. Yeah, we have 30,000 unique. Yeah, 30,000 unique IDs. So this is a large data set relatively. Okay. So that's why this Gridsearch cross-validation took a little longer. But if you can try more variables here, more values there, and then so based on this Gridsearch, which most probably is not going to do a very good job because I'm not exploring it enough. But based on that, the optimal features are going to be entropy, max depth 10, and max features log to the base of 2, and number of estimators, not surprisingly 100 because I only pass 100. Okay, then as in regression, we're going to come up with what I had optimized. We are going to use that optimized predictions versus the actual numbers in the test set. to report the confusion metrics, and then look at the F1 score, accuracy, and etc. Let's compare these numbers, accuracy 48 and 82, with the unoptimized version or non-optimized version. Oh, did I pass it? I think I did, yeah. So 48, 82. This one, 48, 82. We didn't make any improvement, right? The reason is that the Gridsearch was very limited. Okay, so here I just leave it as an exercise for you, but in the homework, you will go over this part. I want you to use cross-validation to estimate the accuracy in the test set. Basically, I want you to estimate this number, 82%, using two methods, cross-validation and out-of-bag errors, out-of-bag observations. Okay, so you can use the random forest regression notebook. The process is pretty much the same. You have to change the name of the score from R2 to whatever you want. Okay, now this is a new thing in classification, dealing with imbalanced target variables, right? Let's quickly take a look again at the balance of the target variable. So we're talking about 80% versus 20%. This is not that bad, given the fact that I have 30,000 observation, right? So it means that my default class has 20% of 30,000, 6,000 observations. So it's not that bad. Usually you are worried about these numbers, which is 98%, 2%, 97%, 3%, 99%, 1%. For those kind of imbalances, there's a good chance that the model is going to always predict one class. So for those ones, you have to be kind of worried, and you either reduce the thresholds, or in random forest, we can use this. Look at that. Let me actually pull up the contextual help. So I'm going to make a new classifier. I call it random forest balanced, right? Everything is the same as before. So again, I just use a random state to make sure that it's reproducible. Entropy, log 2, max depth 10, class weight. This is a new thing, right? So class weight by default is none. So by default, random forest classifier is going to put equal weight on default versus not default. The observation for in different classes, right? If I can change this, let's look at the options to class weights. Yeah, class weights can be balanced subsample, and then if you leave it as none, it's going to be by default, it's going to be none. And let's read through the documentation together. So the balanced mode uses the value of y to automatically adjust weights inversely proportional to class frequencies, right? So for example, here we have 80-20. It's going to inversely give the target variables weights based on 1/80, 1/20, right? It's going to give more weights to the undersample class. It's going to less weight to the oversample class. Does that make sense? So this is if you use balance. Now, if you want to be a little more, so let's call it, I don't want to call it precise. I don't know, more conservative. There is another option called balanced subsample. So the subsample mode is the same as balance, except that weights are computed based on the bootstrap sample for every single tree. Is this clear? So if I use balance, it's going to look at this one and make a balance. So if it is 80%, 20%, okay. If I use the balanced subsample, it's going to look at each tree individually and count the default versus non-default, and then change the weights. Does that make sense? All right. Okay, so that was, again, conceptually, it's easy. If you think that implication is difficult, but Python is easy. You just add a feature, right? So I'm going to call it RF balance. Now I'm going to make the predictions of this balanced model or y hat balance, right? Then I look at the confusion matrix. And then I can look at the report, the classification report. Now look at that. So before cheating and looking at the answer, what do you expect to see? So this is the unbalanced version. What do you expect to see? What will happen to, at least give me this one. What will happen to false negatives? Should decrease or increase? Decrease. Does everyone agree? This is as if you're reducing the threshold, but we're doing it in another way. We are just doing it by changing the balance of the how the algorithm is treating the data. Okay, so 1255 here, which number is going to increase between precision, recall, F1, and accuracy? Which one is going to for sure increase? the recall for sure is going to increase, right? Because false negative is going to decrease. Just go over the definition of recall. It's going to be the true negative divided by true negative false negative. So because the denominator is decreasing, the whole thing is going to increase, right? So now let's see if our observation was correct. So we expect this number to decrease and this number to increase. So this number decreased, yes, from 1200 something, now it's not only 800 something. And recall increased from 37% to 58%. Are you surprised? Not at all. This is designed to do that, right? And precision, what happened to precision? Precision actually decreased because the false positives increased from 333 to 1000 now. And F1, we cannot say, right? Because we have to see which one is dominant. So here it is 55, here it's 48. Here, overall it increased, right? But accuracy is going to decrease, 82%, 79%, okay? Then which numbers should I trust? Most probably these numbers. Because, well, again, this is not that bad. 80%, 20% is not that bad, right? But if it was 99%, 1%, definitely you have to report the numbers for the balanced version of the random forest. Okay. Now that I have the balanced version, I'm not worried about the interpretability of the ROC or if it is legitimate to do it or not. Then I can go ahead and do that, right? So let's construct that our ROC curve. And look at that. Here, I'm going to put the balanced version of the model, right? RF balanced. I'll run the code. This is what we get. So this is random forest balanced version. The AOC is 78%. So it's doing a lot better job than the 50%, chance, random. Basically, this is no skill. And as a benchmark, I think the best we could do with logistic regression was AUC 0.66. So random forest is doing a lot better job compared to logistic regression. Most probably because there are nonlinearities happening in this data set, right? So random forest is really good at taking care of the nonlinearities. Okay, now let's go over the feature importance. And who said limit balance? Well, again, maybe limit balance usually should be important, but I expect it to be more important than none. But in this data set, it turns out to be not that important. But let's look at the output. Guys, these steps are going to be very the same. Oh, actually, the limit to the balance was important. Sorry, my bad. Well, this is not ranked yet. Let's look at the output. Okay, the most important one was if there is a delay in your previous payments, right? So the pay one status is the most important one, and then pay two, pay three. Okay, so in the past 3 months is important. Then the amount of payments in the past month, then the limit balance. So the limit balance was important. Then, yeah, this is something I said I expected to be important. The least important one was marriage status. This makes perfect sense, right? And then sex, education, and age. These are also not that important, at least in this data set. So maybe the data set, you have to look at, so again, you have to do further, dig a little deeper and see if you believe that education must be important, or if you believe that, yeah, let's say if you believe that education is important, you have to look at the range of the education in the data set. If the range is only 4 years, so that's a data issue, right? All right, so that's pretty much it. That's the classification, and we're done with the regression and classification. Is there any questions so far? Are we good? Okay, now let me go over the very last notebook. This is where I wanted to be more clear when I said that the significance that we get from linear model regression is different than feature importance. There's this concept of data snooping. Have you heard the term data snooping? No. P-value hacking. Haven't you heard these terms? Okay. So, well, the idea of data snooping is that, especially it happens in academia, it happens a lot when it comes to econometrics. You have a research question, you have an interesting research question, and on your head, you have an interesting answer as well, right? Does that make sense? You wish the data support that thesis, that hypothesis. Then you start playing around with the data. You have one data set, and you change the parameters or the functional form of the model a lot until you get significancy out of the model for that variable that you're interested in. This is called data snooping. So you work with one data set, and then you make lots of adjustment, optimization, and etc. in the train set to get whatever you want out of that data set. So this is called data snooping. And we also call it p-value hacking. So literally for your econometric project, you were p-value hacking. Now, if you remember, I told you that play around with the model, see which one is most important, put the nonlinearities. Because we were doing all those things in the train set, that was absolutely p-value hacking. Okay. And I don't say it's a bad thing or a good thing, but well, I can say it's a bad thing, but in academia, it's not uncommon, right? Because you have to, I don't know, you have to become a tenure, you have to make publications, so you have to just get. Do you remember this slide? Torture the data, you will confess. So that's the idea of p-value hacking or data snooping. The same is true for machine learning. The reason that you cannot make money out of machine learning algorithm is that it's hugely suffering. All the back tests are suffering from data snooping. So you're optimizing, you're over-optimizing the models in a way that model is going to become, let's say, profitable. You're coming up with trading strategies, and then you say, okay, this is a common theme that you will hear from lots of quantitative analysts. They say that it worked. It worked. I did thousands of simulation and it worked. But as soon as we put it on the real live trading desk, it failed. That's exactly because of data snooping. Okay. And very few, I think very few, handful of hedge funds out there are able to make money. At least the ones that publicly announce that using machine learning. Okay. I think I've said this multiple times before. I don't want to disappoint you. You have to still keep digging and working with it if you're interested in trading using machine learning. But just be aware that this is absolutely very, very difficult to make some abnormal return using machine learning because the data is hugely exploited already. All right, so now that we know what is data snooping, let's see how can we distinguish between statistical learning significancy and machine learning feature groups. For example, I'm gonna make 3 variables. The first one is completely a noise. So this is a normal, it has a normal distribution with, actually it's a standard normal distribution. I have 100 observations, right? The second variable, it's again a standard, not standard, it's normal distribution with the average 5 and variance 5. I don't know, in Python, is it variance or is it, in R, it was standard, it was variance. In Python, I don't recall. Scale, I think scale is standard deviation. Okay, so it's standard deviation. And then variable number 3, I'm going to make a variable off of variable number 2. It's linearly related to that. It's the absolute value of that plus some noise, right? It's a very low volatility noise. It's a normal distribution with mean 0 and standard deviation 0.25. Okay, so these are the variables, right? And now I assume that I'm the God. I know the true functional form between the variables, right? I know that my y is exactly equal to x1 plus x2 to the power of 4 plus x3. I know that, right? So let's construct y. Let's put them in a data frame. So this is a data frame. And let's look at the correlation. Not surprisingly, x1, because it was relatively noise, it's not related to x2, not related to x3, but x2 and x3 are highly correlated, right? 85%. Okay. Now, we can use a pair plot and look at the relationship between these variables. Again, not surprisingly, x3 is the absolute version of x2 plus some noise. So that's why we see something like this. And then the relationship between x1, x2, and x3 with y is something like this. So x1, again, simply a noise. x2, it's increasing, x3 is increasing. So if I use linear regression model, I want you to put your econometric hat on and think about these questions. If I use simple linear regression model, if I regress y on x1, x2, and x3, right? Regress y on x1, x2, and x3. Which one is going to become significant? Look at the output here as well. So consider these variables, and then a very simple linear model. I'm regressing y on x1, x2, and x3. Which one is going to be, well, Let's answer the easiest one first. Which one is going to be the least significant? Does simple linear regression model capture any nonlinearity? No. So it's most probably, if I do linear regression, this is not going to be significant. But if I use random forest, it's going to be significant a lot. Why? Because x2 to the power of 4, and it has a mean of 5, a standard deviation 5. So the entire variation in y is coming from x2. You see that? So let's see if our observation makes sense or not, right? So let's go ahead and use random forest. I'm going to show you the output, the feature scaling first quickly. X2 is the most important one. Made sense, right? We knew that X2 must be the most important one because the average and standard error was large, and it's X2 to the power of 4. So if y is anything, it's getting all the values from X2, and then X3, and then X1. Right? So random forest captures this perfectly, right? Do you see that? So X2, X3, X1. And now let's do simple regression. This is very neat. Look at X2. It's not even significant. Does that make sense? Because it's not able to capture that nonlinearity, right? Then X1, not significant. I'm not surprised here because it's noise, but X3, it's going to be significant. So the linear model is going to say that the next best, well, in linear regression model language, the best predictor out there is going to be X3. And it's fair actually, because the correlation between X2 and X3 was 85%, right? Look how beautifully random forest doesn't care about the high correlation. Actually, if I go ahead, let's actually have some fun. If I go ahead and remove this noise and make sure that the correlation between the two is 100%, right? Well, I have to remove the absolute value as well. Let's say X2 is exactly equal to X3. Right? The correlation is 100%. And then let's see what does random forest do. See, it is still, both of them are relevant. If I do the same thing to the linear regression model, what will happen? Well, in R, it's going to complain and by default remove one of the variables because it has perfect collinearity. In Python, it's going to give you exact same numbers. So here, X2 and X3 are exact numbers. So it says if you have one variable. Okay, so I hope that it shed more light into understanding what is the difference between significance versus machine learning importance, feature importance. These are really powerful stuff. So which one should you use? It depends. What's your research? It depends on what you want to get out of the model. If you want interpretability, go with your econometric model. But be aware that you can leverage machine learning, right? So now I think you realize more when I said that back at BlackRock, we were using machine learning as a check for our econometric models. Because if you're using a variable which is obvious to the random forest in feature importance, but your model is not capturing it, so using random forest is actually a good way to make sure that, let's think about that variable in your econometric model. Again, use as I've always said, use these two in combination with each other. Okay, we're almost done. So have a good weekend, guys, and see you on Monday.